Can people hear me? Yeah, thank you. Yeah, so it's always nice to come and give talks in new places, even if it's not so much of a trip for me. In fact, my office is about 100 meters in that direction. So I'm going to be speaking about two different problems that I've worked on, both of which are related to nonparametric classification. I should confess from the outset that although this is a program on statistical theory and methods for complex high-dimensional data, I will be talking about statistical theory and methods for simple low-dimensional data, or at least fairly low-dimensional data. I think and I hope that the work does have some relevance to high-dimensional problems, partly because for high-dimensional data problems, in practice you might well have a two-stage procedure where your first stage consists of screening several of the variables so that you're left with a fairly low-dimensional problem to deal with in the end. Okay, so the first problem I want to talk about is perhaps some new results on a very old technique, that of k-nearest neighbour classification. And this is some work that I've done with Peter Hall at Melbourne and Byung Park in Seoul. So the setup of the problem is a fairly standard classification problem, except that I'm going to think about a Poisson model for the sample size. So we fix two continuous densities and r to the d, and we assume that we have points that come from a two-type marked Poisson process. That just means that each point in the process either has an x mark associated with it or a y mark associated with it. So the intensity function of this Poisson process is mu f plus mu g. So the mu and the nu are so the average number of points in the Poisson process is mu plus nu, and that's going to be diverging in our theoretical results that we'll come on to later on. And then the probability that each point has a mark x is given by this function psi, which is mu f over mu f plus nu g. Okay, so depending on your point of view, you might regard this Poisson model as a sort of mathematical trick that makes the proofs of the results easier, or you might actually say that in some classification problems it may be more reasonable not to condition on the sample size that you see, but to treat this as random, even though this is a less common thing to do. Okay, so the k-nearest neighbour classifier is a very old, perhaps the simplest type of non-parametric classifier you could think of. The aim of the game is that we wish to classify a new observation which we think of as being another observation from this Poisson process, and we want to try and classify it as coming from one or other of the two populations. And then the k-nearest neighbour classifier assigns this new point z to population x if at least a half of the nearest k elements in our combined sample to z come from the x population. Well, that's a very straightforward rule, but there is a very obvious question that arises from it, which is how should we choose this parameter k, which of course plays the role of some sort of smoothing parameter. Okay, so if we want some sort of technique for choosing k, we should come up with some criterion by which we should measure the performance of our classifier. And a very common way to look at to measure the performance of the classifier is through the notion of the risk or the misclassification error rate. And the misclassification error rate, or risk of the k-nearest neighbour classifier, is given by this equation here. So it's just the prior probability mu over mu plus nu of seeing an observation with the mark x. Then you integrate the probability you misclassify this x observation as coming from the y population. I hope that the notation that I'm using there for the c k-nearest neighbour, that's the way that you classify the k-nearest neighbour classifier classifies the observation z. So we're integrating the probability that we misclassify an x as a y, and then we add on the symmetric term for misclassifying y's as x's. Okay, so as many people here will of course know, this is a problem for which there exists a theoretical optimal solution. If you think to yourself that the probability you classify something as a y has got to be 1 minus the probability that we classify it as an x, then what I'd really like to do is to classify it as a y, is to classify it as an x if mu times f of z is bigger than nu times g of z, okay? Just so that we take the minimum, we get the minimum of these probabilities here at each point. And the classifier we get if we do that, equivalently we can think of this function psi, which I defined on the first slide, as being greater than or equal to half. So then the risk of this Bayes classifier, which is a theoretical classifier, we can't use in practice because we don't know what the underlying densities f and g are, but the risk of this classifier in the Poisson model we get by integrating the minimum of mu f of z and mu g of z divided by this denominator mu plus nu. So what I'm going to be interested in is examining the asymptotic difference between the risk of the k-nearest neighbour classifier and the risk of the Bayes classifier. Of course, that difference will be positive. So, in fact, some very old work by Fix and Hodges in 1951 showed that if the parameter k diverges with the sample size, but in such a way that k divided by the total sample size goes to 0, then the risk of the k-nearest neighbour classifier converges to the risk of the Bayes classifier. That's a sort of 0th order result. It's a sort of consistency result. It doesn't give you any idea of how you should actually choose k in practice. So what I'm going to be interested in here is a sort of first order result to look at an asymptotic expansion for this difference. So this page has some slightly technical assumptions that I don't want to get too bogged down in, but we want to let these sample sizes mu and nu diverge in such a way that they diverge at approximately the same rate. Mu over mu plus nu converges to some p which lies strictly between 0 and 1. I need some assumptions on the nature of the point. I assume it belongs to a compact set. That's another technical assumption. And some assumptions on the behavior of the densities. I really put these up to try to convince you that the assumptions required for these results are relatively weak. We want two continuous derivatives in a neighbourhood of this set S, which actually I've defined a bit below here. This set S is going to be crucial if I can open the chalk. So if I think of contours of the densities looking like this, this set S, these are sort of the weighted contours of densities weighted by these prior probabilities. This set S is really defining the set of points that are going to be really hard to classify, because points out here it's really easy to assign to this population, and points over to this side it's really easy to classify to the other one, but points in the middle are the ones where I'm going to have some difficulty and where I expect to make the most mistakes. Okay. So here is the sort of main theorem for k-nearest neighbour classification. I need slightly stronger assumptions on k than just that it diverges. I need it to diverge faster than some power of nu, and such that k is big O of nu to the 1 minus epsilon, so a little bit stronger assumptions than were required for Fix and Hodges results. But then we have this asymptotic expansion for the difference between the risk of the k-nearest neighbour classifier and the risk of the Bayes classifier. And what we see is that you can write this difference as a sum of two dominant terms plus smaller order terms which we can absorb into this little o term here. these constants here, which I've written as functions of S, this boundary here, really they're integrals of functions of f and g in their first and second derivatives over this manifold, this set, script S. So, and then in the next line, I've just combined these two dominant terms into this function, which I call beta of k and nu. So the first dominant term is proportional to 1 over k, the second to k over nu to the 4 over d. This is sort of fairly familiar from sort of asymptotic expansions for various other non-parametric sorts of problems. And of course it leads to an asymptotically optimal choice of k. So the optimal choice for k is proportional to nu to the 4 over d plus 4. And if I plug this value in and look at what's often called the regret, then that's behaving like nu to the minus 4 over d plus 4. So we have a familiar sort of cursive dimensionality problem where the larger the dimension, the slower the rate of convergence of the asymptotic regret to 0. Okay, so that's a sort of nice result. You might think to yourself that one of the intuitive disadvantages of the k-nearest neighbour classifier is it assigns equal weight to the observation that's kth nearest from the one that you're trying to classify as it does to the one that's actually nearest to the point that you're trying to classify. And once you've had that thought, you might think, well, could I do a lot better than using the k-nearest neighbour classifier if I use some sort of weighted decay on points successively further and further away from the one that I'm trying to classify. And one way that it turns out you can do this is with what's called the bagged nearest neighbour classifier. So bagging is a contraction of bootstrap aggregating and is a sort of very general technique for improving the performance of a predictor, but in the context of classification, you might describe it as follows. So you have your sample of x data, your sample of y data. What you do is to take a resample from that data. Now you have various choices to make. You can either make that resample with replacement or without replacement, or you can take it from the combined sample, or you can do it separately from the x sample and the y sample, but let's not worry too much about that for now. So you end up with a resample, and what you do is you note which way that your classifier would assign the point you're trying to classify if your resample were the actual data that you saw. And the advantage of having made a resample is that I can repeat this process of resampling again and then again and again, and each time I can note which way the classifier, based on the resamples, would assign the observation that I'm trying to classify. And then I can aggregate. So I can just take a sort of majority vote based on the resamples to decide which way I'm going to make my final classification when I feel like I've done enough bootstrap resamples. So the idea is really that you hope that what you gain by this ability to do the resampling and to do the aggregating or averaging process is more than what you lose from the fact that you don't get to choose more data from the true underlying populations, you only get to choose resamples. Okay, in the context of this Poisson model, actually, if you want to bag the one nearest neighbour classifier, or it's often just called the nearest neighbour classifier, then it's useful to think, or the right way to think about it is in terms of just thinning this marked Poisson process. So Peter and I had done some work earlier in which we showed that you can think of the bagged nearest neighbour classifier asymptotically as putting geometrically decaying weights on successively further observations from the one that you're trying to classify. So in this Poisson model, we're going to think of a thinned marked Poisson process where independently for different points, we either kill them or keep them. We delete them or keep them. Okay, and we've got a killing probability of Q. So Q is sort of playing an analogous role to K in the K nearest neighbour classifier. And then the bag nearest neighbour classifier assigns the point to the same population as does the nearest neighbour classifier, but when applied to this thinned process rather than the original Poisson process. Okay, so it's perhaps not that surprising that there's a theorem of a similar type for the bagged nearest neighbour classifier as there was for the K nearest neighbour classifier. We want our killing probability to tend to 1, so we, but not too fast. So that's again analogous to the conditions that we required on K before. And we have an asymptotic expansion for the asymptotic regret, again in the form of a sum of two dominant terms and smaller order terms. And these constants C1 and C2 are the same constants that we had in the asymptotic expansion for the K nearest neighbour classifier. And again, we can group these together. There's a tilde on top of this beta, so the tilde refers to the fact that I'm talking about the bag nearest neighbour classifier rather than the K nearest neighbour classifier. Well then, of course, you can say, well, what's the optimal value of Q, and how fast does the regret decay if you use that optimal value of Q? And unsurprisingly, you get the same rate here, the same rate of convergence, nu to the minus 4 over d plus 4. But what you can also do is to put in these two optimal values for the smoothing parameters, the optimal value of Q for the bag nearest neighbour classifier and the optimal value of K for the K nearest neighbour classifier, and you can look at the ratio of these asymptotic regrets. And what's surprising when you look at this is it doesn't depend at all on the underlying populations, only on the dimension of the data. Okay. So then, okay, well, what does this function look like? If this is 1 here, so this represents, 1 represents sort of equal asymptotic performance. But when D is 1, the bag nearest neighbour classifier does a bit worse. This is somewhere around 1.2. And then when D is 2, it's actually at exactly 1. And then it looks like this. So it comes down to a minimum here at D equals 6. And it's exactly 1 for D equals 2. It's actually below 1 for all D greater than or equal to 3. So I was sort of interested in how much can you improve things in the best case when D equals 6. Not very much. So I showed this to Peter, and he said, well, you know, how much an improvement can you make? I said, well, about 7% on the asymptotic regret. He said, it's not exactly worth selling your grandmother for, is it? No, probably not. But perhaps another surprising thing is that this expression here tends to 1 as D tends to infinity. That may be a bit of a surprise compared with some sort of other results in the literature which suggest that bagging does particularly well in higher dimensions. Of course, when you're looking at these sorts of problems in high dimensions, it turns out that pretty much all the observations are about the same distance from the one that you're trying to classify in high dimensions. So maybe weighting things in different ways doesn't actually make very much difference, or that's my sort of intuition for what's going on here. Okay, so you can also go back and look at what happens in a fixed sample size model. And one way to do that is to condition the Poisson process on the event that the total number of points in the process is equal to its mean. So that's the same thing as taking these taking mu plus nu points and assigning them binomially to one or other of the populations. Well, if you do that and you have the same assumptions as we had before, it turns out that the difference in risk between the binomial and the Poisson models can be absorbed into this smaller order error term here, so that you get, in fact, exactly the same results under these binomial models as you did under the Poisson model. So this work gives you some idea of the structure of the error probabilities of nearest neighbour and back nearest neighbour classifiers. It gives you an idea of the optimal choice for these parameters. It also actually motivates sort of practical algorithms for how you might go about choosing K in practice. And one way you might do that is through the technique of Richardson extrapolation, which is a sort of variant of cross-validation. So we choose a particular power for our resample size, smaller than the original sample size. We apply the K nearest neighbour classifier to the resample and classify remaining data, compute the error rate. So we can do this lots and lots of times based on different test and training data sets. And that would give us an optimal choice of K for a particular total sample size T1. And then because we know the rate at which these things scale with the total sample size, we can incorporate the appropriate scaling factor for use when we have a total sample size of T. All right, so that's the sort of first part of the work that I wanted to describe on nonparametric classification. Are there any questions so far? Well, okay, so to move on, I said that you might think of going from flat weights of the K nearest neighbour classifier to geometrically decaying weights which you get from the bag nearest neighbour classifier. Of course, you're still not using some of the information that you have in the data because you're not using the actual raw distances. You're only using the ranks or the orderings of these distances in those classifiers. So as soon as you start thinking about incorporating the actual distances, you think of actually using some sort of density estimate. So I want to digress for most of the remainder of the talk and talk about a nonparametric density estimation problem. So the problem is very straightforward to state. We have n IID observations that have got some Lebesgue density F0, again in R to the D. And then how should we estimate F0? And of course, the answer depends on what assumptions you're prepared to make about F0. If you're prepared to assume that it comes from some parametric class, then of course we have the theory of parametric maximum likelihood, which does a very good job of giving us an answer in that case. It has the advantage that provided you can agree on some parametric class, and provided there exists a unique maximum likelihood estimator, then you have a sort of automatic procedure for how we should go about estimating F0. You just plug in the density with the parameter chosen to be the maximum likelihood estimator. But of course, it's often the case that we're not that comfortable with putting a parametric form on the distribution that the data have come from. So then if we think about a non-parametric approach, well, the very standard way is to think of using a kernel density estimator. In general, in a d-dimensional case, that requires a choice of a kernel function k, which is very straightforward to choose, but also a positive definite symmetric bandwidth matrix H. So you get a density estimate looking something like that. And the difficulty here is that you've got a half d into d plus 1 choices to make for your positive definite symmetric bandwidth matrix. And this is a difficult thing to do in practice. Of course, in one dimension, it's not so bad. You can just plot a few different, you plot the estimates with some different values and there are also sort of automatic algorithms for how you might choose the single parameter you need in the one-dimensional case. But in the multi-dimensional case, I don't think there are actually any algorithms, automatic algorithms for bandwidth selection, even when d is 2. So I want to ask the question, is it possible to have your cake and eat it? In other words, can we have the sort of flexibility of the non-parametric model that we had in the same way that the kernel estimator worked with a non-parametric model, and yet at the same time have a sort of fully automatic procedure in the same way that parametric maximum likelihood estimators enjoy. If I want to come up with some sort of automatic procedure, then maybe a natural way to do it is to think of the analog of the likelihood function in this non-parametric problem So the likelihood function in this case is just, of course, the product of the density at the observed values, these xi's. Well, what happens when I try to maximize this? Things go a bit wrong, because I could make this is unbounded, this function, because I could make some sort of continuous approximation to just delta functions on all the observations, and I could make this, this likelihood as large as I like. Well, when I think about why I don't think that's a reasonable density estimate, of course it's because I don't really think that all the mass of the density is concentrated in these very, very small neighborhoods of the points that I saw. So it's clear that I'm going to have to impose some sort of constraint on f if I want to get some maximum likelihood estimator here. And the question is, what's a reasonable constraint? So this is some work that I've been doing with my PhD student, Madeleine Kuehl, who's at the back of the audience over there, as well as Bobby Gramercy, who isn't here today but is based in Cambridge, and Michael Stewart, who's at Sydney. So as you'll see, I want to think about the constraint that the density here is a log concave density. That's saying that the log of the density is a concave function. So there are a lot of examples of at least univariate log concave densities. Very straightforward example, the normal mu sigma squared density, where the log of the density is, of course, a quadratic function, but something like a gamma alpha beta density, provided that alpha and beta are greater than or equal to 1. Beta AB densities with A and B greater than or equal to 1. Variable densities, parameter alpha greater than or equal to 1, and so on. So really, in one dimension, you should think of a log concave density as being a unimodal density with pretty light tails. I mean, if you want to think of the exponential distribution, of course, the logarithm there is a linear function, so you can think of that as being like the borderline case. So another reason why, why is this an attractive constraint, apart from the fact that it includes a lot of common one-dimensional parametric families? Well, it has a lot of nice properties. It's closed under convolution, so if you take the convolution of two log concave densities, you get a log concave density. Of course, that's saying that if x has got a log concave density and y has got independent of x and has got a log concave density, then their sum has got a log concave density. It's also the case that pointwise limits of log concave densities are log concave, and so on. They've been used quite a lot in the reliability theory literature because hazard functions of log concave densities are non-decreasing. But actually, remarkably little work has been done on log concave densities when d is greater than 1. And in fact, although this area of nonparametric density estimation under shape constraints has become quite popular recently, I think this is probably the first work that's been done in the case where d is greater than 1. I should point out that the case where d equals 1 of a maximum likelihood estimation of a log concave density when d is 1 has really been covered by Lutz Dumjian, who's at the back of the audience, and one of his students, Caspar Ruffibach. So this work really builds on some of the nice work that they've been doing. Well, there is some interest then in understanding what it means for a density to be log concave in more than one dimension in terms of what it means in the one-dimensional case. And so here's the first theorem that I want to present on this topic. Sorry, could we have the lights off? Thank you. So here's a necessary and sufficient conditions for a density in R to the d to be log concave. It's actually easiest to start with the sufficient condition here. It's sufficient that whenever I look at the conditional density of x given its projection onto a d minus one-dimensional subspace, then that function is log concave. In other words, whenever I take a one-dimensional slice through this d-dimensional density, that should be a log concave function. If that's the case, then my overall density is log concave. Okay? And conversely, if I start with a log concave density, then first of all, the marginal densities of any projection onto any dimensional, any orthogonal projection onto a subspace is log concave. That's not a new result. That's been known since the 70s. But it's also the case that the conditional density of x given its projection, orthogonal projection onto this subspace, is also log concave. So that gives you some sort of characterization of log concave densities in higher dimensions. Okay, well then the obvious question next is log concavity a strong enough constraint to ensure that there exists a unique maximum likelihood estimator of the density? And the answer is essentially yes. And here's the next result then. Well, first of all, I need to assume that n is greater than or equal to d plus 1. Well, that's no sort of constraint at all, really. And it only occurs with probability 1, but I'm not really too worried about that either. So perhaps I should give some sort of sketch of the proof of this result. So what I want to do is to write f for the class of log concave functions on R to the d, and f0 for the class of log concave densities on R to the d. Okay, I want to assume that the convex hull of the data is d-dimensional. So that's an event that occurs with probability 1. It's going to turn out that my density estimate is going to be supported on this convex hull of the data. And in fact, the first two parts of the proof consist of showing this. So if I have a log concave function, not necessarily a density, I want to define what's basically the log likelihood but then I want to take off a sort of Lagrangian term here, which maybe will be familiar from other similar proofs in related areas. So this is the function that I'm going to try and maximize, this function psi n of f. And I claim that if f maximizes psi n, then it must have certain properties. First of all, it must be positive on the convex hull of the data. The reason for this is if it weren't positive at some point in the convex hull of the data, then the concavity constraint on the logarithm of f would actually force f to be 0 at one of the observation points, and of course that would mean that psi n of f was actually equal to minus infinity, which is not good when we're trying to maximize it. So secondly, the density estimate must be 0 outside the convex hull of the data. And this isn't too bad to see either. If it weren't, then I could think about replacing f by f times the indicator function of the convex hull of the data. That would be a product of log concave functions, so itself would be log concave. It would give me exactly the same values for this term, but would give me a smaller integral that I'm taking off here. Okay, so I do better by replacing f with f times the indicator function of the convex hull of the data. The key step in the proof is to think of a finite dimensional class of functions to which this maximizer ought to belong. And to do that, I want to define what I call tent functions. So if I fix a particular vector y in R to the n, I can define a function h bar y. I want this to be the smallest concave function with h bar y of xi is greater than or equal to yi for all I. Okay? It's not too hard to show that such a smallest function has to exist. I call them tent functions because they look like this picture here. So this is a picture when d is 2, and I'm thinking of the observations xi as being along the bottom here. And then with each of these xi's, I associate a tent pole of a particular height. This tent pole, if it's touching the tent, is of height yi. So, and then the function here I get by draping a tent over these tent poles and stretching it taut. Okay? So notice in particular that it doesn't have to be the case that all of the tent poles are touching the roof of the tent. Okay, so this defines a particular, well, I claim that the logarithm of my maximizer here must belong to the class of tent functions. It must be some tent function. And the reason for that is rather similar to the argument I gave before, that if it weren't, then I could replace my f with some function that took the same value at the observations, but had a smaller integral because it's stretched taut here. The concavity constraint tells me that this gives me the smallest integral for any fixed values at the observations. Okay, so that is the big step of the proof, because it gets what was a hideous infinite dimensional maximization problem down to what's a slightly more manageable finite dimensional maximization problem. You might worry about the fact that I'm maximizing over all, actually I'll come over here, over all log concave functions rather than just log concave densities. But it's not too hard to see that actually any maximizer must actually be a log concave density, not just a log concave function. If it weren't, then I could, let's just suppose that the integral of f were equal to c. So I could write f is c times f bar, where f bar had integral 1. And then I claim I'd do better by using f bar than f, because if I look at psi n of f bar minus psi n of f, I get 1 over n times the sum of the log of f bar of xi, and then minus 1 for the integral of f bar. I then have to subtract off the same thing that I get with f, and what you see is you get exactly this same term appearing, but also with a minus log c, and then I have to add back on a c for the integral of f here. And of course these two terms cancel out here, and the function minus 1 minus log c plus c has a unique minimum, takes the value 0 when c is 1 and otherwise it's positive. So I'm better off using the scaled version that gives me a density than I am using the the log concave function to start with. Well then from there it's just a matter of saying, well, I don't do very well if any of the tent poles are particularly high up or any of the tent poles are particularly low down, and it's also a continuous function on this sort of compact set that I get by cutting off the very high and very low values of the tent poles. So I just have a continuous function on a compact set. I can say that it's bounded and attains its bounds. That gives me the sort of existence proof. And the uniqueness proof just comes from showing that the geometric mean, a normalized geometric mean of two log concave densities would do better than the two original things. So that's not too hard to show either. But having shown that these things exist, it's actually quite a challenge to try and compute the estimator in practice. In fact, at this point, Madeline was my part 3 student. She decided to do a project, and I thought it would be reasonable to set the computation of this maximum likelihood estimator as a sort of master's level project. It's about a 6-week project. It wasn't. It was a bit hard for that. And it's taken us, the best part of, well, I don't know, 18 months or something to get something that works pretty reasonably now. Well, the first thing you might think of doing when it comes to finding an actual algorithm for computing this maximum likelihood estimator is to just think about maximizing the restriction of this function psi n to this finite dimensional class. So I could define a function tour of y1 up to yn, and actually when it comes to numerical optimization, people like to minimize functions. So I'm just going to multiply by -1 here and think about the restriction of psi n to this finite dimensional class. Now, the first question you might ask, well, is this a function you can compute? Of course, we've got this integral over the convex hull of the exponential of what's a sort of piecewise affine function that you can see here. It takes a little bit of calculating, but you can actually do this. what you have to do is divide the integral into all of these different simplices. You have to triangulate the convex hull, and you have to map each one of those onto the unit simplex, and then you can establish a sort of recurrence relation that gets you down a dimension each time. So you can write down a closed form analytic expression. It's a little bit complicated, but you can write down a closed form analytic expression for what this integral is here. So I am actually able to compute this function tau for any generic point y1 up to yn. But the difficulty is if you just chuck that function at r in optim and you say, right, have a go at minimizing that, it will bomb spectacularly, right? If you just have sort of 10 points in 2 dimensions, you run something overnight. One of the interesting things about the problem is you do actually know, or you have some idea of when you're getting close to the right answer, because this integral should be getting close to 1. Okay, so that's a difference from quite a lot of numerical optimization problems. But you look at the first iteration, you see an integral of 0.95, and you think, okay, this is good. Maybe this is going to work okay. You come back overnight, and it's got to 0.953, and you think, oh, well, that's maybe not quite so good. So we needed some new way of thinking about this. One of the difficulties or the 2 main difficulties. First of all, optim doesn't really use anything anything about the structure of this function, and also this function from y to h bar of y is not an injective function. So many different tent pole heights could potentially give me the same tent. In particular, if something's not touching the roof of the tent, I could just move it down and I don't change the function. So there's no unique minimum minimum value of y1 up to y. It's not a unique minimum value, that's what I'm trying to say. So the next idea was, if I don't like that function, well, let's just change the function that I'm trying to minimize. And I only change it in a subtle way, but it turns out to be quite important. I only change the first term, and I just do it by replacing h bar y by yi. And the reason that that's a good thing to do is because it means that the function sigma is actually a convex function. So I now know something about the structure of this function, and it's greater than or equal to tau. That's not so important. It's got a unique minimum now, so I've got some better chance of being able to locate it well. Well, just changing the function you're trying to minimize, it wouldn't be any good unless it were the case that the logarithm, the maximum likelihood estimator that I'm looking for, is actually this h bar at the y star that minimizes this function sigma. So changing the problem was a good start. Convex functions are nice for optimization because you have all this technology of Newton's method and steepest descent methods and things like that. And I was thinking, okay, now I'm back in business. It turns out that there was another snag in the problem. In fact, it became a bit of a soap opera from this stage. The problem comes from the fact that this convex function isn't actually differentiable. So we can't, well, at least we are going to have some difficulties with things like Newton's method. The reason it's not differentiable is due to this second term here. And what you see, if you imagine you're at a point where this tent pole is just touching but not critically supporting the tent, then if you move that tent pole down, you don't change this integral at all, whereas if you move it up, then you change the integral by an amount that's sort of asymptotically proportional to the amount by which you'd move the tent pole up. So this is a non-differentiable convex function. You might say, well, you know, it's only a set of measure 0 where it's not differentiable. Maybe I can just forget about that set of measure 0 and chuck it at Newton's method. No, it bombed spectacularly when we tried to do that. Of course, every function is almost, every convex function on R to the n is almost everywhere differentiable. So maybe that should have given me some clue that that was a dumb thing to do, but it didn't. So things boiled down to trying to minimize this non-differentiable convex function. I didn't know too much about how to do that. But fortunately, we then came across this book here, which is called Minimization Methods for Non-Differentiable Functions. In fact, it doesn't have the word convex in it, but it should really say it is all about convex non-differentiable functions and minimization methods for convex non-differentiable functions. That seemed like a good book to get me going at this point. It's written by Shaw, who's working in the Soviet Union, and written in 1985. And he came up with the idea of a subgradient method. So a subgradient method is based on generalization of a gradient. If you imagine a convex function, this is supposed to be some sort of kink here. If you're at a point where you're differentiable, then there's a unique subgradient at that point which is equal to the gradient vector. If you're at a point where you're not differentiable, then you potentially have multiple, well, then you do have multiple subgradients. They're all the gradients that would give you a tangent hyperplane that supports the function. It's probably easiest to describe with a picture than anything else. So you always have at least one subgradient you have at any point. You have a unique one if you're differentiable at that point. Otherwise, you have more than one. And Shaw's idea of the subgradient method was just that you needed to be able to find one at least any one at an arbitrary point, and then you can use the following algorithm. You take a sequence of step lengths which go to 0, but quite slowly in such a way that the sum diverges, and then you just move along by an amount by that step length, but in the direction of the subgradient vector. So this is sort of an analog of a steepest descent method for differentiable convex functions. It turns out that this is not necessarily a descent method. So although the general trend for this algorithm is to go towards the minimum point, you don't necessarily go down at each stage. This algorithm is nice because you can prove it converges in a nice way, but it turns out to be very slow when you try and implement it. So we were getting a bit frustrated by this point. Fortunately, Shaw realized that it was slow in this form, and he came up with a variant of the subgradient method that's become known as the Shaw's R algorithm. So the problem with the subgradient method as it's in its original form is that if this is the optimal value you're aiming for, then you tend to sort of spiral around it. These subgradients can be in a direction almost orthogonal to the point that you're actually trying to head towards. And so the idea for the R algorithm is to examine the successive differences between subgradients and to incorporate a sort of space dilation feature to try to get you a direction that's somewhat closer to the point to which you're trying to converge. And this was implemented in some C code by Kapil and Kuntsevich in 2000. And finally, when we sort of adapted the code to work with this, we did get something that worked reasonably. So to give some very quick demonstration of this. So there are 4 lines here. We've loaded our R package, the log-conc-ded package, log-concave density estimation in arbitrary dimensions. The RGL package is just a sort of surface plotting software. We've generated 500 bivariate normal observations, and we've computed the MLE. And if we plot the output, it just takes a few seconds to come up with the density estimate. So and here it is. And you see the points and you see the density estimate. You may not be able to see, there's just a little point here where you can see the edge of the convex hull of the data here. You can rotate things round. You can look underneath it. All sorts of things like that. So I hope that convinces you that this is a sort of a reasonable density estimate. As a final very quick extension, you can think about using an idea which George Chang and Gunter Walter used in a recent paper, where they thought about fixed fitting mixtures of log concave densities, finite mixtures of log concave densities, they did this in one dimension. We've now been able to extend it because we've got an algorithm for computing the maximum likelihood estimator in more than one dimension. We can extend their algorithm, which is based on the EM algorithm, to fitting finite mixtures of log concave densities. And this has some potential for clustering and things like that. So to show you briefly how this works, I am going to show it in one dimension where it's easiest to see what's going on. So here we have an example of 500 observations plotted along the x-axis from this mixture of two gamma densities. I think they're gamma 2,1 densities, which are log concave densities. One's shifted along by 5 units. So a natural starting point for this clustering algorithm is to fit the finite mixture of Gaussians. And that comes out like that. Of course, you can't expect it to do very well. These are skewed densities. It's got no hope of being able to capture that skewness with the Gaussians. And in particular, notice how far it gets the point where these densities cross wrong. So these cross here rather than the true densities crossing here. So all these observations will be misclassified if you're using it for classification. Let's see what happens when we move on and do the fitting of log concave densities in conjunction with the EM algorithm. So if we just do one iteration of this algorithm, you get to that point there. You can see we capture the peak of the second density component much better, but we haven't really got the skewness yet, so we sort of iterate. And you can see it sort of adjusting. And you notice how the point where these densities are crossing is getting much closer to the true density crossing point there. Okay, and it's done there. Okay, so in conclusion, here's another potential non-parametric density estimation technique. It's fully automatic. There are no smoothing parameters to choose, and yet it is a non-parametric method. I think it has some potential as a classifier. Of course, if you want to use kernel density estimation in classification problems, you have to choose bandwidth matrices for all the populations you're dealing with. So there's, again, further attraction to having a fully automatic method, something like that. Well, there are many other related problems that Madeline and I are working on at the moment related to this log concave and shape constrained density estimation idea, but I'll stop there for now. Thank you very much for your attention.
Any questions? We'll take a few questions before.
Yeah.
Right.
In the first part of your talk, you had a rate of 4/4 + d. There is a paper by Charles Stone, I think from '82, regarding minimax rates of approximating functions, which has exactly the same rate, and I'm wondering how is it related or not?
I think I'd need to check that paper exactly to confirm that. But you're not going to get a better rate for this sort of classifier than n-4/d + 4. Whether the constants are, I don't know whether they specify constants in that paper.
I don't either.
No, I need to check it.
More questions? Okay, we'll break for now. We're back at 30 minutes.
Thank you for dealing.